Hi everyone. If you want to build your RC heli with Graupner's newest Flybarless system, the Hawk 18, I've got you covered. In this video I will show you the entire setup process, from start to finish, or as we pilots say, from binding till takeoff. No, nobody says that. Anyway, let's get started. In order to have a solid foundation and achieve good flight performance later on, it is important to set everything mechanically, as precisely and symmetrically as possible. The servo horns should be positioned to match the center position of the servos. All linkages need to be at a 90-degree angle to each other, and the swash plate must be at 90 degrees to the main rotor shaft. Since most helicopters are slightly higher at the rear, I always place my mechanics on a few wooden blocks. This ensures that the main rotor shaft is exactly vertical. This will be important later when calibrating the rescue mode of our Flybarless system. If you have a 3D printer, you can also print the helicopter setting aid I designed. The link is provided below in the description. This tool allows you to align your helicopter quickly and easily. Instead of charging the flight battery and risking the engine starting, I prefer to use my charger as a power source for the receiver. I arrange the channels as follows. The swash plate servos are on channels 1 to 3, the tail servo on channel 4. Channel 6 is assigned to the throttle or the ESC. The controller's telemetry comes in on channel 9. These channels are fixed. I still have 2 BEC power sources and my backup battery remaining. I connect the backup battery to channel 8, which is still free. A BEC cable is connected to the free channel 5, and the second BEC cable goes to channel 7. This means all the channels are now utilized. However, since it makes sense to have the power where it is needed most, especially near servos 1 to 4, I prefer to put the second back line together with the servo on channel 2. That's the plan. Before powering anything in the helicopter, we first need to create a new model in the transmitter. We use manual mode rather than the wizard. To pair the receiver with the transmitter, we first click on Base in the transmitter menu, then on TX control. Next, we supply power to the receiver to initiate the binding process. After about 15 seconds, the receiver's LED starts flashing red, indicating it is ready for binding. We then simply click on the search field at RX1. As soon as a value appears here, the receiver is bound. The LED on the receiver will now show a steady green light. First, we want to program the engine off switch. To do this, we click on Base, then THR Cut, and assign a switch. Click on G/S and move the switch you want to assign. Then define the engine off position. Finally, unlock this function by clicking the top field. Now, you will receive an immediate warning when switching on the transmitter if the motor switch is accidentally engaged. Additionally, as a second safety measure, I use a throttle limiter controlled by a rotary knob. This is because a single switch can easily be accidentally flipped by a jacket sleeve while handling the model. To set this up, go to the Base menu, then to CTL Set. Click on the field for channel 12. This channel is reserved for the throttle limit function. Next, assign the desired control. Done. Finally, we verify the function of both switches using the servo monitor. When the engine off switch is active, no throttle signal is sent on channel 6. Only when the engine off switch is deactivated and the throttle limiter is enabled does the controller receive a signal. If we close the throttle limiter at full throttle, the signal returns to 0 as expected. This double-layer safety approach is much better. Let's move on to the flight phases. Currently, the throttle channel is still linked directly to the pitch value. However, later we will set up a horizontal throttle curve because the main rotor speed should maintain a constant value. Since we want to fly at 2 or 3 different speeds, we set up different flight phases that can be switched during flight using a switch. To do this, click on Function, then Phase. By default, one phase already exists, which is always active unless another phase is selected. My plan is to have 3 phases, one for autorotation, one for normal flight, and one high-speed phase for 3D flying. To add a second phase, for example autorotation, we click on Phase 2, then on New. Since autorotation is already the default name here, we just need to assign a switch. Click in the field and move the desired switch. Then select the switch position that activates this phase. Next, we add a third phase for 3D flying. We also need to rename these phases appropriately. Click on the phase name, then on the NAM field, and enter a new name. I'll keep it short and simply write 3D. You can see the currently active phase by the green text at the top of the screen. To avoid sudden changes between phases, we add a small delay. This makes the transition smoother and prevents the helicopter from jerking around. We should also set an audio announcement for each phase. Click on Set at the top, then click the corresponding field for each phase and choose a suitable announcement. So far, the flight phases only differ by name. Next, we'll configure their throttle curves. Click on Function, then Throttle Curve. Now, when switching flight phases via the switch, you can select the throttle curve for each phase. Starting with Phase 1, the normal flight speed, I want it set at 65% throttle. Click the throttle curve, then on Y-axis, and move the throttle stick down. Adjust the points using the plus and minus buttons to set the desired values. Repeat the same for the maximum throttle value. Move the stick up and adjust the point to 65%. Next, switch to Phase 3, Aerobatics, and set the throttle curve to 80% throttle. The exact values can be refined later. Sometimes vibrations occur at certain speeds, but disappear a few percentage points higher. It's worth experimenting here later. I haven't set the autorotation throttle curve yet. To program the ESC properly, I'll need a throttle curve that goes from 0 to 100%. I'll cover this later when configuring the ESC. While we're at it, let's define a switch for the rescue function, which is assigned by default to channel 5 on the Hawk 18. Go to Base, then CTL Set. Select channel 5, click the box, and move the switch you want to assign. Since rescue mode activates only when the throttle value exceeds 100%, we need to adjust the servo travel. Go to EPA, select channel 5, and increase the value to 125%. For completeness, Set the counter deflection to 0%, though this step is optional. Finally, check the proper functioning of these settings using the servo monitor. Now, I would like to set 2 more clocks to display the flight time. I can either click on Clocks in the base menu or long press on the respective clock to open its settings. The first clock should run backward, showing a countdown of 8 minutes. To do this, I set the mode to T-. I set the alarm for 8 minutes. The clock should start simultaneously with the engine, so I use the engine off switch as the trigger. Go to CTL, move the switch, and select the desired switching position. The clock should also stop when I turn the engine off again. Therefore, I assign the same switch for clock stop. The second clock should simply run forward, but be resettable. To do this, long press on the clock below, then select the same switch. Also, assign the switch for clock back. Next, we briefly check the failsafe settings. These activate as soon as the connection to the model is lost. We are particularly interested in the throttle value, so switch to channel 6 on page 2. Change the mode from hold to position. With the throttle limiter turned off, click on the field and then on set. The new value is now applied. Since these settings cannot be transmitted if the radio connection is lost, they must be saved on the receiver. To do this, click on SP. Now the values are stored in the receiver. Okay, that was a lot. Let's move on to the Flybarless settings. Now we plug in the 3 swash plate servos, but not the tail servo, because it has a different center pulse, and we first have to adjust it in the FBL. To set up the FBL, we click on Base, then on Telemetry, and then on Set View. I won't go through all the settings now, only the most important ones. Let's get started. The model type is, of course, a helicopter. The cycle time can be shortened to 10 milliseconds with modern servos. On channel 9, we want to connect the telemetry from the controller, so we need to select sensor there. Next, we go to the last page for axis assignment. To do this, we have to skip a few pages. We set the new setting to Yes. Then we control roll to the right and tilt the helicopter to the right. Same with pitch forward. And with the tail to the right. Then we need to calibrate the gyro orientation. It is important that the main rotor shaft is exactly vertical. Otherwise, the rescue function will not work properly later. Now let's go back one page to the basic settings. We can leave the direction of rotation to the right, swash plate angle to 120 degrees, and servo frequency at 200 Hz. Now let's check if the swash plate changes height with pitch. The direction doesn't matter at first, but it doesn't. Instead, we have a nodding motion. So we increase the value by 1 and see if it improves. Now it tilts sideways. Raise it by 1 more. Okay, now it moves up and down. Very good. Now all we have to do is reverse the direction. To do this, switch briefly to the basic menu and change the direction of channel 1. In my case, we also have to do the same for roll and pitch. Now the swash plate operates as it should, and we can switch back to the FBL menu. Next, we want to align the swash plate exactly horizontally to the rotor shaft. I printed a suitable swash plate gauge using a 3D printer. You can find the printing data in the description below. Alternatively, you can buy one or use the cable tie trick. Now adjust the value until the swash plate is perfectly at a 90-degree angle to the main rotor shaft. Do this for both roll and pitch. Now the rotor head can be mounted next. Now the rotor head can be mounted next. In order to conveniently read the blade adjustment without the rotor blades installed, I printed a small holder for the digital pitch gauge. You can find the print data for this in the video description below. Now set your pitch to exactly 0 degrees. Alternatively, you could slightly loosen the 3 linkages. However, you would then need to check the alignment of the swash plate again. So I'm opting for the simpler method here. Next, set the maximum cyclic deflection to 8 degrees. To do this, normally you apply full roll deflection and check whether the blade above the tail boom shows 8 degrees. To make it easier to see in this video, I'm demonstrating with pitch deflection instead. Unfortunately, I had to remove the transmitter from the picture, otherwise I wouldn't be able to read the value. But I think you understand the process. There's still a little adjustment needed, so I increase the value until it reaches 8 degrees. Now we set the desired maximum pitch value. You can find recommended values in the instructions for your mechanics. I'm setting 13 degrees here. If the helicopter feels too aggressive for you, you can reduce these values later using a pitch curve. Set the values for pitch stick up and pitch stick down accordingly. With the swash plate limit, check whether the swash plate or rods start to bind at the combined maximum deflections of pitch and roll. Move the sticks fully and listen for unusual servo noises, or visually inspect if anything seems off. Next, I adjust blade tracking by checking whether both blades have exactly the same pitch value. I am very precise about this. If a blade angle differs, simply adjust the rod length until they match. This is easy for me because I have turnbuckles. Alternatively, you may need to remove a ball head and screw it in or out. Both blade angles are now identical. Perfect. Now I set the tail servo to its correct center position. This value is usually indicated on the servo packaging, or sometimes marked on the servo itself. Now you can finally connect the tail servo. You can immediately check whether the servo direction is correct. Pushing the stick to the right should cause the rear sliding sleeve to move to the left. The tail frequency is correct for my servo, so I don't need to change this value. Let's move on to centering the tail. I adjust this so that the rear sliding sleeve sits roughly in the middle. With most mechanics, this corresponds to an angle of attack of around 3 degrees. The performance of the tail rotor depends not only on the angle of attack, but also on the gear ratio and blade length. However, our FBL system will handle the controls later anyway. Therefore, an approximate center position is sufficient here. There are 2 values to set for the rear limit: the maximum end positions without any mechanical binding. To switch between these values, simply move your control stick, then adjust the values as needed. Let's move on to the rescue function. Here we set the direction and travel distance of the swash plate, that is, the pitch movement. Since I have a servo reverse on pitch, I have to set a negative value here, so that the swash plate moves up. A value between 60 and 70 is a good starting point, which you can adjust during the first test flights. The larger the value, the more aggressively the helicopter rises during the rescue. Since I'm using rescue, I set the logging to 0. This way, you can display the Euler angle via telemetry. Now let's talk about tail sensitivity. This value must be experienced. If it is too high, the tail will start to swing. Therefore, I like to have this value controlled flexibly via a rotary control. This lets me adjust it during flight without entering the menu. To set this up, go to the CTL Set menu and link the rotary control for tail sensitivity to channel 7 and the rotary control for swash plate sensitivity to channel 9. Go back to the FBL system settings. When changing a value, keep clicking until the channel linked to the rotary control appears. This way, the value can be adjusted during flight. Do the same for swash plate sensitivity on channel 9. Once you reach your desired value, use the servo center setting on channel 7 or 9 to set the servo center of the rotary controller. This is practical when flying multiple models alternately. Now we can check that the FBL is working correctly. Hold the helicopter and tilt it in all directions. The swash plate should try to compensate for this movement and remain horizontal. The rear sliding sleeve should also attempt to maintain its position in space. If you move the tail to the left, it should move slightly to the right. Now I remove my temporary power supply and connect the ESC receiver signal and a back line to the FBL. Next, let's start configuring the controller. Switch to the Autorotation phase with the linear throttle curve and deactivate the engine stop switch and throttle limiter. Now throttle equals pitch. Set the throttle lever to full throttle. Connect the battery to the controller. Wait for the continuous interval tone. When a confirmation tone sounds, you are in the controller setup menu. Set the throttle to 0. Wait for the desired mode. Mine is mode 2. To select it, go full throttle again. After confirmation, bring throttle back to 0. The controller is now armed. Accelerate carefully and monitor the tail rotor. If the motor turns in the wrong direction, change that in the controller settings. Connect the controller to the USB adapter. Click Connect and plug in the battery. First, change the motor's direction of rotation. Set the battery cell count to 12 and the BEC voltage to 8.4 volts. Continue to the next page. Enter the correct number of magnets for the motor and the gear ratio. The precise speed can be calculated based on these values. You can find this information on the motor manufacturer's website and your mechanic's instructions. On the following page, select the correct telemetry protocol. For Graupner, this is HOTT. Finally, set alarms. I am particularly interested in the capacity-used alarm. I fly batteries with 5,200 mAh, so I want a warning when 3,800 mAh has been used. Write the changes to the controller. That's it. We're done here. Now let's move on to the final settings. After programming the controller, we can adjust the throttle curve for the auto-rotation flight phase. Return to the Throttle Curves menu, select the auto-rotation phase with the switch, and adjust the values. I choose 15% instead of 0 for a faster bailout. Let's briefly discuss dual rate and Expo settings. These let us influence control curves, making them stronger or weaker, sharper or softer. You can customize them individually for each flight phase. First, select the aerobatic flight phase. DR defines the maximum control deflections. Since we have an FBL system managing deflections, here we're dealing with rotation rates, how fast the model rotates around an axis. Because this helicopter is relatively agile and powerful, I reduce this slightly on the first flight to avoid being overwhelmed. I set it to 90% and enable symmetric control of both values with sim set to on. Then I define the Expo value. This softens rotation rates near the center of the stick. A good starting Expo value is 20%. Set this separately for all three axes: pitch, roll, and tail. Then repeat for the other two flight phases. Since we've set Expo in the transmitter, ensure the Expo in the FBL system is set to 0. Programming is now complete, and I can finally lay the cables. With the cables laid, it's time for the first flight. I hope you enjoyed this video and found it helpful. Please leave a like or subscribe. It motivates me to continue creating this content. Bye.